I like to have props. So these are my props I'm going to use today for Physics in 24 questions. Question number 12, chapter 13 from Halliday Resnick and Walker. I'm not even going to show you the book. I mean, if you're jumping in right here, I mean, I don't know what else to tell you. So let me go ahead and tell you the problem I'm going to solve, and then we'll talk about a whole bunch of physics. But I'm going to first make fun of this chapter title, Gravitation. I mean, it just seems kind of like, I don't know. I wouldn't name it gravitation. You know, you could call it gravity even would be better. Gravitational forces, things you can do with gravity stuff. I don't know. Just throwing out some ideas there for the 10th edition. Okay, the problem. Number 81 from chapter 13. So we have a binary star system, two stars of equal masses. They have a mass of 3 times 10 to the 30 kilograms, and they're orbiting a center mass. They're both 10 to the 11th meters from the center mass. A, what's the angular velocity of the system? B, it's kind of a weird question. They say if a meteor passes through the center perpendicular, how fast does it have to be going in the middle to have an escape velocity? Because if it's passing through, then it already escaped. Whatever. Okay, whatever. I'm going to solve that one anyway. So we got a bunch of stuff, a whole bunch of stuff here. There's a whole bunch of, they crammed this chapter packed full of stuff, and I'm not going to use it all, but I'm going to at least mention it. I'm not deriving it, remember. The main goal here is to solve that problem. But I want to talk about this stuff because I love it. And bonus, this one may be a little bit longer. I'm going to do a Python calculation for that too, because why the heck not? Why not? Okay, we got a lot of stuff to do and very little time. The first thing is this idea of gravity. Gravity as an interaction between, here's my props, right? An interaction between two objects, mass 1, mass 2. There's a gravitational, we can model a gravitational force attracting those two that depends on the mass and the distance between their centers if they're really small. So let's go ahead and write down that gravitational model, because that's what this gravitation thing's about, gravitation, right? So here's M1, I'll put this over here, here's M2, and I will give credit to the book, they do this right. Let's make this the vector R. So R is the vector from mass 1 to mass 2. Now, if you have the vector positions of these two, let's just for fun, let's say this is R1, this is R2, then R is going to be R2 minus R1. I can write the gravitational force on 1, F, as negative G, M1, M2, over the magnitude of R squared, R hat. You have to have that R hat, and I applaud the book for including R hat. A lot of them don't do that. So here's the gravitational force. But if you don't include R hat, you just have the magnitude, and it's not nearly as cool. So just a reminder that R hat is a unit vector in the direction of R. We could find that R hat as the vector R divided by the magnitude of vector R. But now that's a scalar, scalar, scalar. I have to take the magnitude of R squared to find the R squared, and then I don't have a vector, so I have to multiply by R hat. And the negative sign just means that it's in the opposite direction of R. And then mass 2 would have an equal and opposite force. So that's the gravitational force. G is a constant, 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. Fundamental concept. Okay. Superposition. Superposition is a really important thing in that if I have more than one mass and I want to find the mass on a particle over there, there would be a vector gravitational force with that interaction and with that interaction. So the total is just the vector sum. So let's call this F1, F2, and this is F. So F is just the vector sum of those, F1 plus F2. And it turns out to be a really big deal, and it shows up in electric fields and all these other things. And while I'm at it, I would like to do something. The book doesn't, I glanced through and it didn't look like it did this. If I have an object right here and I have a point in space, I could calculate the gravitational force on a mass right there. And let's say this is big M and that's little m. So it's going to be negative G big M, little m over r squared r hat, right? That's r hat. Well, we also have the g, little g, as a vector, and it's going to be the gravitational force on a mass m divided by that mass. So it's the force per unit mass. This is what's called the gravitational field. And I think it's important to mention that because in later chapters, when you're talking about the electric field, this is the basic same idea. And so it's important to get used to that principle. And so the units for G, the gravitational field, are in units of newtons per kilogram. It's the force per unit mass. Okay. They talk about this, they say gravitational force, I'm pretty sure. I would talk about gravitational field. What if you're, we like to deal with this, that's a point mass and a point mass. They don't have to actually be points, but they have to be far enough away that we can treat them like that. But you can't always do that. And there's a great problem that's an example, but I'm not going to solve it. And it has to do with the gravitational field inside of the Earth. So if this is the, or any planet, if this is a spherically distributed object, and there's a center, and so it has a radius of r, and I want to find the gravitational field at some point inside. Well, it turns out, through some complicated math, that the only mass that matters is the mass that's closer to the surface. So if you break this up into a bunch of individual point masses and add up the gravitational field through superposition, over here, these outside pieces are going to contribute more, they're going to be stronger gravitational fields than on this side. But if I look at right here, there's more of this stuff farther away than there is closer. But the end result is all the gravitational field from that stuff cancels. So we don't have to worry about it. We only worry about the inside. So you don't have an increasing gravitational field toward the center where, you know, if we did 1 over r squared, as r goes to 0, it goes to infinity, that'd be bad. And then they talk about this famous problem of making a tunnel through the Earth and falling. I'm not going to do that problem. Great problem, though. Really great problem. I actually have done that problem. And that same idea shows up in electric fields when we talk about Gauss's law. It's really Gauss's law for gravity. You don't really need to know that, but it's in there. I want to mention it. I'm not going to derive this, but remember that if a force is conservative, if the work done does not depend on path, then we can make a potential. And we can make a potential for the gravitational force as negative g m1 m2 over r. Now that's the magnitude of the distance between m1 and m2 to the center. And the negative sign is really important. And this says that we pick a potential of 0 at an infinite distance away. Okay. Yeah. So that's the gravitational potential. I didn't derive it. I can derive it. But again, we're trying to, I got a bunch of stuff to do. Next, escape velocity. We can use that for escape velocity. So escape velocity, really quickly, if I have a planet of mass m and a radius r, and I have an object that I shoot with some velocity v. So using the work energy principle and the system of those two things, work is a change in kinetic plus a change in potential. And there's no work done because it starts with some initial velocity v1 at a position r. And we want it to get an infinite distance away with 0 velocity. So we can put all that in here. I have k2 minus k1 plus u2 minus u1 equals 0. So really far away, 0. Really far away, 0. So now I have minus 1/2 m v1 squared minus a negative, so plus g m. Well, that's capital M, I guess. Capital M, lowercase m, over the initial position r is equal to 0. So that cancels, and I solve for v1. I get the square root of 2g m over r. This is what we call the escape velocity. If you're going that fast on the surface, you will leave and never come back. And it doesn't even matter what direction it is. Remember, work energy is a scalar problem. So you don't have to move away. You can go in any direction, and you'll never come back. Okay. Useful for deriving stuff for black holes. moving right along. Kepler's laws. You know, I wouldn't put Kepler's laws in here, but there's the sun, and here's a planet. Kepler's first law says that the path of this planet is an ellipse where the sun is at one of the foci. Okay, so ellipse. 2, this is equal area law. This is weird, but this says that, well, it's not weird. Kepler did not use models of physics. He didn't use Newton's second law. He didn't use Newton's law of gravity. He just said empirically the data says this is true. Okay, so this says that as a planet moves around right here, as it gets closer to the sun, it's going to go faster. Over here, it's not going to go as fast. And so, but if you use the same amount of time, this area is equal to that area. And you can derive that as conservation of angular momentum, but that's what that says. And then finally 3, this says t squared is proportional to r cubed. And so this one's really hard for non-circular orbits. It's not too bad for circular orbits, but this says that the period of orbit squared is proportional to its semi-major axis cubed? I can't remember, but there you go. Those are Kepler's laws. Last thing before we get into our awesome physics problem, which is indeed awesome, is the equivalence principle, Einstein's equivalence principle. I can't spell it. Is it va or va? Equivalence? No. Just write it messy and no one will even know, right? So this is really important. It says that if you are in an elevator on the Earth like that, then you feel a gravitational force and an upward pushing force like that. If you then take that same box and you put in deep space some rocket engines on it, and it accelerates this way with a value of g, then you will still have that normal force pushing on you like that. And if this is a closed box, you can't tell the difference between an accelerated reference frame and a gravitational field. And so you could use this to say, well, then gravity is not even a really force anyway. Fine, okay. We can still model it as a force and get a lot of great things done. But that's what the equivalence principle says. We're not going to do any problems with it, but it's pretty cool. See? Let's see, how long did that take? 12 minutes just for the intro. Wow, we're going to be here all day. Hope you got some popcorn ready because we got some stuff to do. Now we can do the problem. Here, I'm going to draw this. Here's one planet star. Here's the other one. There's the center of mass. Okay. Let's calculate the angular frequency for this system. So if I look at this star right here, it has a mass m. I'm going to call this just capital R, the orbital radius, and it's moving with some velocity v. What forces are acting on that mass right there? Well, there's a gravitational force pulling that way, F. And that's it. So let's write Newton's second law in this position right here. Okay, I'm going to call that just at this instant, I'm going to call that the xy direction, the xy direction. So in this case, I can say F net x is going to be the gravitational force, which is going to be negative, it's in the negative x direction, negative g m, right, because it's due to this, divided by how far away is that? What's the distance between these two? Well, it's 2r squared. Right? Okay. And that's going to be equal to the mass, which is it's accelerating in this direction. And it has an acceleration of v squared over r, right? Because it's moving in a circle of radius r, not 2r. And we could actually use the angular velocity version of that and say this is negative m omega squared r. See, that's not such a bad problem, right? But it's going to be cool. We're going to do great stuff. So now I can just solve this for omega. The negative signs cancel. That mass cancels with that mass. It's weird. Okay, that's fine. So I get omega squared is gm over 4r squared. And they need to divide by r, so I have another r cubed right there. And then so omega is the square root of g m over 4r cubed. That was pretty easy. Okay. Now the next problem, I'm going to put that over here. I didn't even calculate it because I didn't get the number. Square root g m 4r cubed. We can test it with our model. Okay, now for the next part. Suppose that I have a meteor right there in the middle and it's moving with some velocity v, and I want it to escape. Well, in this case, I can use the work energy principle. So I have the system star plus meteor. I think they said asteroid. Because technically, a meteor is a rock burning up in the atmosphere. So since I have all three objects in there, I get two potential energies for the asteroid, right? I'm going to see these don't change their potential, right? Because they don't change position with respect to each other. But I have a gravitational potential energy between that asteroid and that star, and between that asteroid and that star. And I have kinetic energy for that, kinetic energy, but these kinetic energies don't change. The asteroid is small. It's not going to disturb the problem, okay? If it was, it'd be a big problem. So I can say there's no work on the system. There's no external forces. Work is going to be the change in potential energy. I'm going to sum them up together, plus the change in kinetic energy for just the asteroid. So I know I want to find the initial kinetic energy, escape velocity just like before, and the final kinetic energy 0 to escape really far away. So also the final potential energy 0. So I can write this as 0 u2 minus u1 plus k2 minus k1. So 0, 0, just like before. But the only difference is now I have to find the gravitational potential due to both stars at that point. So u1 is going to be the potential due to the interaction between these two. I'll use m1 for this mass. So I get negative g m1 over the distance between them r. And then for this one, I get the same thing, minus g m1 over r. So that's going to be negative 2g m1 over r. Now I can set that equal to the initial kinetic energies. Plug in my stuff. I have 0 is negative of that, which is going to be 2g m1 over r minus 1/2 m1 v1 squared. And I want to solve for v1 squared. Mass cancels. So I get v1 squared equals 4g m over r. v1 is going to be 2 square root of g m over r. That's my escape velocity. I have to fill in my chart here, otherwise I don't get full credit. So 2 square root of g m over r. Okay. Let's now model this. Now the asteroid's going to be a little bit more difficult to model. Let's just do the binary star and see how it's going, because we're already at 19 minutes. We got time. You don't have anywhere to go. If you don't have time, pause it. Come back later. It's the internet, right? Okay, so here I have my asteroids. No, they're stars. Oh, that's a bad circle. How can I model the motion of these? Because the problem here is that, yeah, they're moving in a circular path, and that's fine. And this is pretty easy. We already calculated the initial angular velocity. I can calculate this velocity, right? The magnitude of that velocity is going to be r omega. We looked at circular motion before. And I can calculate the gravitational force. But now I want to calculate the force wherever they are. So what I'm going to do is to calculate the force on this one based on that. And then I'm going to calculate the force on this one. And then I'm going to break it into a short time interval. And I'm going to use the momentum principle. So the momentum principle says F net is the change in momentum with respect to time. If that's a short time interval, like, I don't know, a day. I don't even know what time, how short it has to be. Let's just pick an hour. We'll see what happens. That's an hour. Then the forces are not going to change too much over an hour. Okay, so I can use that to say this is P2 minus P1 over delta t, where P2 is the momentum at the end of the time interval and P1 is at the beginning. So now I can solve for P2. P2 is P1 plus F delta t. So I can update the momentum of that one, and I can do the same thing for that one. And then I can use that momentum and find the velocity to update the position using the same idea. So let's call this position A and B. So I can say R, let's just write it out. P A over M is delta RA delta t. So if I do the same thing, I get RA2 is RA1 plus PA divided by M delta t. So now I have a new position. I'm going to get a new gravitational force. And I just keep doing the same thing over and over and over and over and over again. I flew through that really quick. Okay, but I really just want to show it to you. So let's do that. Let's build these two orbiting binary stars, and then we can play around with it and see what happens. I'm not going to do the asteroid thing because it'd be a lot more explanation. I had to have to calculate the gravitational force between all of the things, and I just don't want to do that. I really just want to show you Web v Python. So I'm switching over here to Web v Python. Gonna give you the code. You know I'll give you the code. I'm a code giver. So let's start off with some constants. So G is 6.67 times 10 to the negative 11th. I'm not going to put units just for time. M is 3 times 10 to the 30th, 3e30. And then R, capital R, is 10 to the 11th. 1e11, not 10e11. Okay. Let's go ahead and make our two stars. I'm going to put the origin, the center at the origin. So just to make things easier, we can make it not that way. But so let's call this star A, SA. It's going to be an object of type sphere. Its position is going to be equal to vector r0, 0. So on the x-axis at a location r. Now the radius, I'm going to have to guess here. The radius of my star, if I do, let's do r over 20 and see if that, it's going to be I'm going to make it bigger than it should be so we can see it. I'm going to give it a color dot yellow, and I'm going to give it a trail. Make trail equals true. And let's just run it and see what happens. So there's my one single star right there. See it? I might need to zoom out there. Okay. Now let's do the other star. I could just copy this whole thing. Watch this. Copy, paste, call that B. And the only thing I'm going to change is I'm going to put it at negative R. So now I have two stars, star A, star B. Good. Now I need to give them some initial conditions. I can't update the momentum if I don't have the momentum. So I'm going to start off with, let's calculate V0. I just said it was r times omega, and omega is that. So I'm going to say this is equal to r times the square root of, I'm looking over here, g times m divided by 4 times r cubed. Yep. So star A's momentum, SA, is going to be equal to the mass times the velocity vector. I want it in the positive y direction, 0, v0, 0. And then for star B, it's going to be the same mass times the vector 0, negative v0, 0. Oh, you got to type that right, 0, 0. So it's going to, that one's going to be going up, and that one's going to be going down, right? Okay, I need t. I need dt. I said it was 1 hour, so that's 3,600 seconds. This is the hard part, right? Because we're dealing with forces and momentums in kilograms, meters, newtons, and seconds and stuff. So, but it's a longer time scale. Let's just say while t is less than, I'm just going to pick a value. I don't even know what I'm doing. E1 times 10 to the 5th. And I'm going to pick a rate of 100. So rate 100 tells Python how fast to animate things. So we can change that and just display things. The first thing I'm going to do is to calculate the vector. I'm going to call it RAB. This is the vector from A to B. So it's going to be SB.POS minus SA.POS. So SB is an object. Dot POS is the position of that object. Dot P, oh, I messed up here. I didn't put the dot P. Dot P. Dot P. Dot SA dot P is the momentum of that object. I can assign properties to these objects like momentum and position and radius and color and make trail. Okay. So that's the vector from A to B. Now let's calculate the force. I'm just going to call it F. It's going to be equal to negative G times M times M times, right? I need that unit vector. I'm going to put it right here. And in Python, there is a built-in unit vector called norm. Now I need to divide by the magnitude of that vector. Again, built-in, mag RAB squared. So that's the force on A. Wait, let's see. So it's from, I did from A to B. So it's a vector that way. The negative sign. So it's on B. That's the force on B. So let's use that to update B's momentum. SB.P equals SB.P plus F times dt. And now I can update the momentum for A. SA.P is SA.P minus F times dt, because it's the same force but in the opposite direction. Finally, I need to update time. T equals T plus dt. Now, you'll notice what happens when I go through this. I have to recalculate my position vector, my relative position vector, so that will recalculate the gravitational force. Also, if you haven't seen something like this before, this equal sign is a make equal to sign. So I'm updating that value. Those things don't cancel. Let's just see if this runs. If this runs, I'm going to give myself a double high five. Okay, it must be too slow. Let's do rate. Just double it up. And let's go down here. I can't even tell when it's done. So let's say print. And that's the hard thing with working on different time scales. It's hard to just judge. There are ways to calculate it, but okay, so it didn't go very long. Let's do this for 10 to the 7th. It didn't take very long. 8. Oh, I know what I did wrong. Okay, I did not update the position of the objects. I forgot that part. So let's update their position. SA.POS is SA.POS. I was just too excited. Plus SA.P times dt divided by m, and SB.POS is SB. You got to emphasize that word too. Plus SB.P times dt divided by m. Okay, sorry about that. I was just excited. It's my own fault for being excited. There you go. Look at that. And you'll notice that they are indeed circular orbits because we assume that with our initial velocity. Just for fun, let's try changing the initial velocity, decreasing the velocity by 0.9%. I'm just picking a value. So over here, I'm going to multiply this by, let's say 0.8. I changed my mind. So it's going to be lower than it needs to be for circular orbits. Let's see what happens. Notice they still orbit, and they are circular. These are circular orbits, but they don't orbit around the same object. Okay, so that's kind of fun to do. And you can change the masses, you can do all sorts of stuff, but this is the idea of a numerical calculation. I just want to show that to you just because it's so cool. And there's a perfect opportunity to do that. It's not in the book, bonus. I'm going to save that. I'm going to give you a link to that code down below, and that's gravitation. Hope you had fun with gravitation. Next problem, next chapter. Talk to you later.